We welcome Professor Eric Vazquez, who is going to talk about overview of dark matter experiments.
Thank you, and thank you for the invitation. I would like to also thank Carlos Sandoval. I want to give an overview, a biased overview, I would say, about direct detection of dark matter. You have been hearing in the morning about the results from LHC, searches in LHC, and Alejandro Ibarra will talk about indirect detection. So I'm going to focus on direct detection. This is the overview of my talk, the outline. Since I saw that half of the auditorium are students, so I prepared a brief introduction to what we do in direct detection. Then I want to show some techniques, one for spin dependent and one for spin independent, PICO and DEEP. And then I guess I have to show a little bit about xenon. I have three slides about that, and then my final remarks. So all this comes to this pie chart of the universe, coming from an impressive number of observations at different scales pointing to this missing matter in the universe. I always like to summarize most of the evidence going from galactic rotation curves of galaxies, X-rays, gravitational lenses, and then the CMB and even simulations of large-scale structure. So basically this is what we know about dark matter. It interacts gravitationally, it has to leave, it has to be stable or long-lived. And you can see here the list of what we know. It's basically pointing to physics beyond the standard model. And there's a huge range of cross-sections and many possibilities, and I want to focus on two of them. There are actually more theories than theoreticians, and if you randomly pick one of these, there's a 50% probability that I actually don't know what it is. But there are many theories behind it. So two candidates attract the attention of the community. There's actually a bias towards WIMPs. I am on this side actually, but I see no reason. Both candidates that are being studied provide solutions to something else besides dark matter, and but I'm going to talk about WIMPs. So basically, this is the most discussed candidate produced in the Big Bang in thermal equilibrium, and then it decouples as the universe expands. It's very rare that they find each other to annihilate, and then in principle we would have some of them, a few per liter, depending on the mass. And we actually don't know. I mean, it is true that there are some expectations from SUSY models. There are many more models, and we don't know the coupling to this dark sector, which could be as rich as the standard model. So the detection methods, I'm going to focus on wind scattering, direct detection, and as I said, on Thursday you will hear about indirect detection. Alejandro will talk about it, and we already have seen some results about accelerator base. This is basically how to detect it, shake it, break it, and make it for the search of dark matter. And this is a summary of what we do in direct detection. We basically look for the scatter of one of these WIMPs with the nuclei, and then we detect the recoil energy. The recoil's energies are of the order of a few keV. And then we calculate the rate based on some assumptions. Historically, also there are many more possibilities, many more interactions. We search for two couplings. One is called spin independent. That's basically a couple to a nucleus. And so it's enhanced for large nuclei. And then we also look for spin independent, that basically couples to the spin of the nucleus. And this is a cartoon of what actually happens. So you have one of these WIMPs, and there's a scatter in this nucleus, and this nucleus moves a few nanometers, and we search for energy depositions of a few keV. There's one problem, and that's our backgrounds. Neutrons, for example, produce exactly the same. There is no dark matter experiment that can discriminate between these energy depositions in nuclei coming from WIMPs or neutrons. And then you also have electromagnetic interactions. Those go to the electrons. And we actually try to separate, to discriminate between these two. And this is a summary of the rate calculation. So it basically has four pieces: the dark matter density, where we have the mass of the dark matter particle, the unknown particle physics component, the cross-section that I showed here in the spin-dependent couplings. And then you also have the nuclear part and the velocity distribution. So we put all these together with some assumptions. We measured the number of events, and then what you have seen is this plot of the cross-section versus the mass. And here is some area that has been ruled out by the experiments. This is the coherent neutrino scattering function, the floor, neutrino floor. And then there are a few models of generic WIMPs and asymmetric dark matter. So how to catch a WIMP? So basically this is what we look. We live in a dark matter halo with some density, and the WIMP comes and we look for this tiny deposition. And the problem is that there are many backgrounds. There are neutrons, muons, gammas, beta decays, alphas, and neutrinos that produce similar energy depositions. And we are looking for one event per ton per year, less than that value. And we have 10 to the 11, 10 to the 12 events per ton per year. So we have to reduce all these backgrounds, and there are three things that we do. One is that we go underground. We shield our detectors, and then we do a careful selection of the material with which we build our detectors. And we have been able to reach these levels actually, and I will show you some results. And this is basically the recipe for to do a dark matter direct detection experiment. So you are looking for these tiny depositions, a few keV. It is important because it depends on the threshold at which you can measure this energy. So it varies for different isotopes. You need to do your background suppression, and that's you go underground to reduce the cosmic ray flux, and then you have the shielding, passive and or active, and then the selection of the materials. And then one thing, here are three examples. I'm not going to focus in these three because I'm going to show for pico and deep what we do, but it's basically to separate the nuclear recoils from the electron recoils. Once that, and you scale your detectors, and we are now at the ton scale targets. So that's basically what you need for a dark matter experiment, looking for direct detection. And I'm going to talk about just two of these briefly. One is going underground. So we always like to show what it is going truly underground. And this is, I'm going to use as an example the place where Pico and Deep are located. This is a snow lab, 2 kilometers underground in northern Ontario in Sudbury, in Canada. About 5,000 square meters of laboratory space. And this is the snow cavern that you heard 2 years ago about the Nobel Prize to R. McDonald for the oscillation of neutrinos. I have a few pictures, but I think that it's always nice to actually see a video of what it is going underground. So that's what I have to show you here. As I said, the first part is for the students, so they see about what it is doing physics underground. So the cage travels at about 40 kilometers, 50 kilometers per hour. It takes 5 minutes to go underground, and you go with a lot of miners because it's an actually active mine. They are extracting a nickel underground, and you can clearly see the difference between a physicist and a miner right away. So it's not complicated. And once you are underground, there is about a mile, 1.5 kilometers that you have to walk to the entrance of the lab. And the lab is a class 2000 environment. It's basically a clean facility where the air is being removed and exchanged, cooled down and filtered. And inside, everything that goes inside of the lab is clean at that level. So basically to remove any dust, that could go into the lab. As you can see, when you have $1 million lab and you go with a camera, you record 2 guys with a couple of buckets, right? That's what they did. This is the deep experiment that I will show you briefly. This is the cavern when it is located in the Cube Hall. Just 2 years ago, when we were deploying the resurfacer that I will briefly talk. This is Deep 3600. It is actually the largest operating dark matter detector now. We have more than 3 tons of argon in there, a few vents that we have. Well, this is basically what it is like going underground. And I'm gonna move because time is running. So this is the entrance to the lab, and you need to take a shower once you go underground. This is the coffee room, the lunch room, and everything here was clean, perfect, with great precision. Even Stephen Hawking got a chance to go underground 3 years ago, actually twice. He went in the 90s and also 3 years ago. And of course there was a special car to take him underground. And as I mentioned, this is the home of the Nobel Prize, 2015 Nobel Prize in Physics, one of the experiments to Arthur McDonald. So this is one thing, go underground. The second one is something that we should care about. There are 3 things that we should care about, basically. And that's backgrounds, backgrounds, and backgrounds. If we don't reduce them, we basically cannot claim any possible discovery. And maybe to give you a sense of what it is, what are those backgrounds, this is the reactivity is coming from the surroundings, from the detector materials, and even activation of cosmic rays. So here are some comparisons, and so how much radioactivity is in our body, what is the most radioactive food that we eat, for example. And well, here are the answers. This is the 10 to the 11, 10 to the 12 events that we get in our detectors. I mean, it's not coming from this. I mean, this is just a comparison. And so all these energy depositions from components, which are huge. It's, for example, 1,000 becquerels from the coffee. Coffee actually is forbidden outside of the lunchroom. Well, any food is forbidden. But there was a huge discussion with the former director about having or not coffee underground because it is very radioactive, and just a few grains of coffee could be catastrophic for one of the detectors. But you have to wait between having physicists at 6 a.m. without coffee and tools, or having coffee. So we have coffee underground. And basically we have to remove this 10 to the 11, 10 to the 12. We cut down basically 6 or 7 orders of magnitude in this number by going underground. This is the muon intensity versus the depth. So Sudbury is here, so you go like 6, 7 orders of magnitude down in these backgrounds. Then with the shielding and the careful selection, you basically avoid these muons and neutrons produced by muons. And this is, for example, what it looks like germanium detector spectrum once you put some shielding and purge the detector with nitrogen. So you cut down another 3 or 4 orders of magnitude. And then besides the discrimination, and this is basically a summary of all the backgrounds that we have coming from cosmic rays, decays in the thorium, uranium, and potassium chain. So once we have achieved all these, we can go and do some physics with our detectors. This is the first part of my talk that I told you. This is where it ends, that I showed you about the techniques and what we do in underground physics. And I'm going to show you now results and a dedicated look at one of the experiments. So this is the PICO experiment, which search for dark matter with superheated liquids. This is the collaboration. This is actually the collaboration meeting last year in Mexico, where institutions from Canada, US, Mexico, India, and the Czech Republic. And this is basically our detector. We use a bubble chamber, those similar to those ones used in the 70s in particle physics. But here, while we have these fluids, we have been operating our detectors running with CF3I and C3F8. You could actually make a bubble chamber with any liquid. And this is a cartoon. You have a pressure vessel, stainless steel. Inside you have a synthetic silica quartz jar where you keep this superheated fluid. And what happens is that once you control the pressure and the temperature, you basically set the thermodynamic parameters of this detector, you are sensitive to particles. Those particles make a transition, phase transition, and those produce bubbles. And we have four cameras that take pictures of those bubbles. Once that happens, we quickly compress our detector so to recondense the fluids. And besides that, we have 8 piezoelectric acoustic sensors. It's basically fancy microphones, and I'm going to tell you why we use that. We have these microphones listening when the bubble is produced. How does the nucleation works in these fluids? Well, it's a competition between the surface energy and the latent heat. And basically what matters is that the bubble production not only depends on the energy, but on the stopping power, on D and dx. So what that means is that if you have a region where a bubble can be nucleated, electrons and gammas basically are outside of that window. Or we can actually tune our detectors to put them outside. And that's because even if they have enough energy, they don't deposit that energy within a certain critical radius. And that's important because then that means that we are insensitive to electrons and gammas, and we have measured it. This is the probability of nucleation. This is 10 to the minus 11, and this is the threshold of our detectors. And you can see here for 2 fluids, CF3I and C3FA, how we have been able to achieve 10 to the minus 10 discrimination in the production of bubbles coming from electrons. So basically that we're removing all the electromagnetic interaction from our detectors, and what we have is alpha decays, neutrons, and hopefully WIMPs. These are pictures of our detectors. This is our latest chamber that I will show the results. It's a chamber of about 1 meter tall and 20 centimeters diameter. And there are a few events. You can see here 1, 2, 3, 4, 5 bubbles taken by our cameras. We're basically recording the most boring movie in the world, because you only see once in a while bubbles coming in the detector, and that's it. Actually, these multiple bubbles were produced by neutrons, because they have a mean free path of a few centimeters, they can produce more than 1 bubble. So we can produce 1, 2, or 3, 4 N bubbles. And WIMPs, we expect that it will be 1 bubble, and alphas, it is 1 bubble as well. It's basically a nuclear recoil and an alpha track of 40 micrometers. So what we have to discriminate is basically 1 bubble from this know-how if it belongs to one of these 3. And here's another event also obtained with a neutron source. I challenge you to count how many bubbles, and I'll invite you a beer tonight at dinner if you tell me how many bubbles are here. It's 20. I always rush because it is a close number, and maybe somebody will tell me that it is 20 bubbles, right? Well, I told you about that we have these piezoelectric acoustic transducers, and the reason is that single bubbles produced by alpha decays are louder than those ones produced by nuclear recoils. To the camera, they look identical. You cannot distinguish one bubble if it is coming from a neutron or an alpha. But the Picasso collaboration discovered that alphas are louder. And you can think that in the case of a neutron, the neutron interaction, it's basically a nuclear recoil. It's the neutron coming, hitting the nucleus, and then the nucleus recoils a few nanometers and deposits a few kV. Right? And that gives us a macroscopic bubble. And the alpha decay, it's a similar macroscopic bubble that grows, basically. But besides the nuclear recoil, you have the alpha track that does these multiple radiating bubbles. At the end, when you see the image, they are identical, but the power that has the acoustic power, it is larger. And these are alphas and these are neutrons. And this is our acoustic parameter normalized. This is the WIMP region basically obtained with an ambisource with neutrons. And these are alphas. Actually, you have 2 peaks corresponding to alphas of different energies. So this is something that we use to discriminate, to separate the alpha interactions from the neutrons. And in that receipt that I showed you about dark matter detectors, so this is a summary for PICO. We have a threshold detector. We cannot measure the energy event by event, but we can do a scan, of course, at different thresholds. The suppression, while we are underground at Snow Lab, we have an active passive shielding of water, and we did a clear selection, careful selection of the materials. And then the background discrimination, we're insensitive to electrons and gammas because of the thermodynamic parameters of our detectors. The neutrons, we can discriminate the multiple bubbles or know that we have a neutron background, and the alpha, we discriminate them with the acoustic parameter. And so we have been scaling out detectors. Actually, I will show you the family of detectors that we have. So here are a few numbers that probably are not, I don't tell you that much, but I will show you a summary in a few slides. But the first question is why bubble chambers? Well, we use bubble chambers because of this electromagnetic insensitivity and this alpha acoustic discrimination. We basically have a zero background detector if we eliminate the neutrons. We are building or designing, actually, we have funding for our ton scale detector. Now we are operating detectors of a few 50 kilograms, 60 kilograms. We are able to use multiple targets. And that's very important. We have used fluorine and iodine, but a group at Northwestern has basically made a xenon bubble chamber. We are working on an argon bubble chamber, and collaborators in Montreal are actually developing an hydrogen, a compound with hydrogen bubble chamber. And as I said, we measure the nuclear recoil energies by changing the threshold, and we don't have information about the nuclear recoil direction. And spin independent is attractive for many reasons, but basically this is for the effective theory, the response that we see that for fluorine, because we have this unpaired proton, that we are sensitive to the longitudinal and transversal spin-dependent interactions. This is a summary of the fluids. Fluorine is better for sensitivity to spin-dependent interactions. This one, the iodine, bromine, xenon, argon enhances, exploits the A-square dependence for spin-independent, for example. And the hydrogen will allow us to go into low wind masses. And we basically can explore the spin-dependent and spin-dependent independent with our chambers. So this is the family of our detectors. We started with a CF3I 2-liter bubble chamber 8 years ago, and 7 years ago, and then we moved to a 40-liter. We changed fluid to C3F8 to focus on the spin-dependent, and we run a 2-liter and a 60-liter detector. We are preparing a 40-liter that we are deploying right now at Snow Lab, and it will be operating on early 2018. And as I said, we got funding for the PICO 500, and that's our ton scale detector. So this is the family of our detectors. This is 2 liters, this is 40 liters, and this is 2 liters again, and this is 60 kilograms, about 40 liters. And we're preparing this PICO 40 with a different technology. And this is, for example, how the spin-dependent wind proton coupling cross-section we have been measured over the years. So you can see this is actually much better than Moore's law, and these are our detectors. The battery died, but I think that there is another one here. This is Picasso, and this is our 2-liter chamber with the C3F8. This is the result that I will show you that we published this year, 2017. This is what we expect for PICO 40L next year, and this is where we expect to reach with PICO 500. These plots are based on using C3F8 and for a 50 GeV wind mass. But of course, we have this variety of fluids that we could use, as I mentioned. Actually, I need to use both. Okay, I only have 2 hands here. These are some pictures of our latest detector, the one that I'm going to show you the results. Pico 60, this is the chamber, 1 meter tall. These are the acoustic sensors during run 1, and this is when the detector went inside of the pressure vessel. This is the water shielding tank to basically stop all the neutrons from the rock. And these are the ports and the LED illumination for the cameras to take the pictures. And so we filled our detector with 52 kilograms of C3F8 on June. We started the physics run on November and we ended it in January, only 2 months. We collected almost 1 ton day of dark matter rich data at this threshold. And then we performed, instead of a blind analysis, we actually did a deaf analysis. So basically we turned off the signal from the acoustic sensors. So we didn't listen to the bubbles that were produced there. And this is the result before we unmasked before we opened basically the acoustic parameter signal. We had 106 events. And once we opened our window, we found no nuclear recoil candidates. And this is basically the acoustic parameter with the alphas. All of them were consistent with alphas. That's what I'm trying to explain. And we basically placed some limits. We lowered our limits by a factor of 17. This is the spin-dependent coupling. And for spin-independent, because we have light targets as carbon and fluorine, we place some limits here at low WIMP masses. When we showed these, we got some comments about the CMSSM model that we were using that was outdated. And we actually, it's not official, but somebody just put what Professor Ellis showed in the morning or something similar. And we basically placed our limit that in case of these models that tell us where we need to go with our next detectors, right? With Pico 40L and Pico 500. And to compare with the LHC limits, we talked to the dark matter working group, and they gave us some recommendations on simplified models that go depend on the dark matter mass, the mediator, and the both couplings. And this is what we can do for some standard values for an axial vector mediator. And this is basically Pico, and this is CMS. So this is the result that we just published this year. The next detector, we are switching the technology. It seems that we were operating our detectors upside down, so we flip it because we had some anomalous background. And this is Pico 40L. We expect to basically demonstrate which engineering technology we are going to use. And actually, after 1 year background-free exposure, this is where we could go. Let me explain you here. This is the spin-dependent coupling. The blue one is the result that I just presented. And this is to spin-dependent to protons. You can also see from LUX, but that's to neutrons. And this dotted blue line, it's Pico 40L. And then the one below, it's a Pico 500, our tone scale detector, which is at the level of LZ for spin-dependent, but coupled to neutrons, basically. So something interesting from our detectors is that this is a neutrino floor. And you can see that the gray one is for xenon, which is different for C3F8. So basically, in our case, with our detectors, we still have 2 or 3 orders of magnitude before reaching the neutrino floor, the coherent neutrino nucleus scatter. And that makes our detectors very interesting. Besides that, we are developing also, as I said, xenon and argon bubble chambers. And interesting in these detectors is that we could operate these detectors at thresholds of 100 eV, for example, not keV, because our C3F8 chambers operate at 3.3 kV, but these ones at 100 eV electron volts, and that basically gives us reach to low WIMP masses. And this is a Pico 40L the pressure vessel on the surface at SNOLAB. This is a cartoon of, we are doing the design of Pico 500, and well, this is, I already showed it in the previous slide. This is a picture of our run in 2017 at SNOLAB that I just showed you, but I think this picture is really cool, so I wanted to show it. Okay, so this is the spin-dependent section of my talk for Pico, the dark matter leading detector actually on the spin-dependent for direct detection. Now let me move to spin-independent. And for that, I'm going to talk about deep 3600, and we use argon to search for dark matter. And so this is a collaboration. We are 65 researchers from Canada, UK, Mexico, and actually I'm forgetting Germany that recently postdoc moved up to Germany, and so there's she's participating also in deep. Why do we use argon? Well, liquid argon is a scintillator. Besides, the suppression of electromagnetic events is done by what is called the pulse shape discrimination. I'm going to talk a little bit about it. And also, there are some advantages for having a large liquid argon detector. It is well understood. It can be purified easily. And we have a uniform response. And we began with a 7-kilogram prototype that I will show you some results just to build my physics case. And then I'm going to show you the results of deep 3600. And this is what I was mentioning. This is a 7-kilogram prototype. And basically, the difference, this pulse shape discrimination is because the electromagnetic recoils, pulses, are different from the nuclear recoils. They have a different lifetime. So these ones are shorter, and these are longer pulses. And we use that in this plot to basically determine the amount of charge in the prompt part of the pulse. And what you can see, this is the electromagnetic. These are the nuclear recoils, and this is the electromagnetic band. And with that, we separate the nuclear recoil interactions from the electron recoils. So this is underground at SNOLAB, the prototype that we had, 7 kilograms. This is an old picture now. Lots of these pieces now were just basically scavenged to deep 3600. And this is where we are now, deep 3600. It's a single-phase liquid argon experiment. We have 3.6 tons. Actually, we have only 3.3 tons of argon now in the detector. We have a wavelength shifter because the PMTs basically see light at a different wavelength. We have 50 centimeters light guides to separate the room temperature which the PMTs are operated from the liquid cryogenic liquid argon. And then we have our detector immersed in an 8-meter water shield tank. And before I show you the results, I'd like to emphasize on this careful selection of materials and of the backgrounds. So this is the cube hole. This is where the deep 3600 is located. And this is basically how we built our detector. It's an acrylic vessel of 85 centimeters radius, so 1.7 meter diameter. And basically, there is one place in Thailand that could build this in a radon-free room environment. And 4 pieces were shipped you cannot take them by air because cosmic rays activate the acrylic. So we take them by sea, by boat, and once in Alberta, in Canada, in an oven, they are basically assembled. Then it is moved to SNOLAB because it was not enough to fit in the cage. It had to be put underneath. So it was slinging below, underneath the cage. And then this is when it went to the cube hole. There, what we did, we started basically gluing the light guides, the 50 centimeter light guides. And then you put more shielding here, polyethylene blocks, and then you start coupling the 255 PMTs. In between, you allow the National Geographic to go and take a picture. And this is how it looks like before the water tank shielding was filled. These are the Vito PMTs and calibration tubes. And this is how it evolved when we constructed. Besides, talking about backgrounds, we had to basically build a robot made of pure materials with low radioactivity to basically remove a few microns of acrylic, because the vessel was exposed to radon air, air from the mine, and that has lots of radon. And that basically plates in the detector and implants isotopes of lead. Basically, we had to remove those isotopes. So this is how careful we have to be about our backgrounds in direct detection. And here are a few events recorded when we turn it on. There were some issues, we had to fill it twice for some issue with a part of the near the neck. We have tested or checked the linearity, the energy response with calibration sources. And let me show you, of course, we also have optical sources, lasers, LEDs. And since last year, we have 3.3 kilograms of liquid argon. We have more than half a year of data that we will publish early next year. But these are the results from 44 days of data that we published last July. And basically here in blue, it's our result. It's basically the best limit from an argon detector. And in red, you can see dark side 50. These three are log xenon, and actually they put Panda X. Panda X results not from this year. Actually, they are already here. But this is what our projection for 3 years with argon. So we expect that next year, when we publish about a year, we will be very close to these xenon detectors. I have about 5 minutes. Perfect, because that's more or less what I want to show. Basically, this is I already showed about these generic wind models that we will be able to explore with Deep 3600. But probably, but besides the results that I'm showing you, there is a new argon collaboration formed with all the experiments doing liquid argon for dark matter. Dark side, deep, mini clean, and RDM. So we have now a joint collaboration for a 20-ton liquid argon detector at Gran Sasso. With underground argon, surface argon has argon 39, and that's basically giving us lots of backgrounds and basically saturating our detector, the detectors. And also a joint collaboration on a multi-100-ton detector in the mid-2020s. In a site to be determined. And this is where we could, well, this is actually, this is a cartoon of dark side 20K. This is one person, just to give you an estimate of the size of the detector. You cannot see it, that's one person. And this would be a model for a 150 tons liquid argon detector that we are working. So we are supported by a few underground labs, Gran Sasso and Snola, for example, and it has been well seen, this collaboration. And this is what we could do, for example, with dark side 20K. We will be at the level of LZ with xenon, and then a multi-ton detector for 1,000 ton years, we would place us basically at the neutrino floor. So the argon community is growing, and I guess where all of us are going in the same direction in these multi-ton detectors. The difference is that, well, this is a two-phase, dark side is a two-phase argon detector, and deep is a single one. So my last, I only have a few slides, and I guess that since xenon is the xenon detectors are leading the field, and for a review, I couldn't avoid showing something about xenon. There are 3 experiments, LOX. It's basically, it's located in the US in some state in the Davis cavern, actually. This is a two-phase detector, in the difference from deep that uses only scintillation. Here there is an electric field, and besides the scintillation, you have also a gas phase for the ionization. And the experiment or the collaboration is now building a larger detector, LZ, with 8 tons of xenon, and this is one of the xenon detectors. And the other one is xenon 1 ton, is also a similar detector, two-phase liquid xenon detector. This is in Gran Sasso. And I guess I don't have slides about Panda X, which is another xenon experiment. I thought that 3 xenon experiments in a talk was too much, so I only put 2. Instead of that, these are the results published actually early November in this month. And you can see the limits from xenon and from Panda X, how they are at the level of 10 to the minus 46 square centimeters. So this is where the xenon detectors are right now. You could also see similar limits in the argon, but of course at low cross sections, at WIMP masses of 50, 100 GeV, the xenon detectors are leading this field, and you can see here actually the limits from log xenon and Panda X from the latest results from this month. Okay, and of course there is a world of dark matter searches. There are different labs. I didn't talk about germanium detectors or gamma, sodium iodine crystals, but there is a world community working on dark matter. And finally, I think that this is my biased opinion of where the field is moving. I think that experiments have momentum to keep building larger argon and xenon detectors, but I guess this is it is very interesting. The people are moving increasing the size of the detectors, but they are also moving to lower thresholds and atomic masses, basically to explore low WIMP masses. So that's basically the trend on WIMPs. But this is just a tiny fraction. Here you can see all the orders of magnitudes in energy, and I only talked about this small fraction. Maybe a few GeV, but this is basically what we do in direct detection. Yesterday we hear about the axions, but there's a window of opportunities everywhere. And for example, just to give you 2 examples, this is the same plot that I've been showing you. For example, these are all these detectors, xenon, argon, pico. Well, this is spin independent, but anyway, pico. And people are exploring low thresholds, like in an argon bubble chamber, where you could go to EV and you could reach this area, for example, for low WIMP masses. But there is an open window here where people are looking for ideas to explore. And even in axions, and I found very interesting this paper about axion-like dark matter through nuclear spin precession in electric and magnetic fields, where they have been able to look for the interactions of 10 to the minus, masses 10 to the minus 21, 10 to the minus 18. So people are exploring other ideas. And I guess this slide is just to show you this community working on different areas at different energies, which I actually am not an expert on this, so it was just to make my case. So I only have 2 slides. Could be a neutralino, an axion, an S-neutrino, and this guy, well, he has a different opinion, right? What it could be. My conclusions, my final remarks actually, I was going to put some conclusions about what we do in PICO or in DEEP, but I tried to make a general description. Well, dark matter could be, well, WIMPs, axions, both, maybe. I think that it could be as rich as the standard model that we have, right? That's the more natural thing to think, I guess. I'm optimistic, always. And while multiple discoveries will constrain its properties, I mean, signals from direct detection, indirect detection, colliders, I mean, it could be like a dream. Multiple detectors and techniques are required. And as I mentioned, the backgrounds are the most important thing that we care about. Backgrounds, backgrounds, backgrounds. And of course, we should be open for new theoretical ideas and new experiments. So who knows what it is just hiding behind us. Thank you very much.